So this lesson is intended to help explain and make students understand how to determine the sign of a function. We will be looking for a linear function, a quadratic function, and from there we'll extrapolate to think of an odd degree polynomial and even degree polynomial. So for a linear function, as we're going to be looking here, we're going to see that we have to consider two cases: if the slope is positive or if the slope is negative. We have an example here, y equal x plus 1, for the slope being positive. This is where the slope here is equal to 1, as you can all see. This expression, y equals x plus 1, has an x-intercept at x equals negative 1. And we're not going to be interested in the y-intercept, just the x-intercept. Since it has a positive slope, the function will start from quadrant 3 and it ends in quadrant 1. So as you see, the function starts from being negative in quadrant 3, it crosses the x-axis and changes to positive. And if you look for the slope as a negative value, we'll look for the example y equal negative x plus 1. Here the slope is negative 1. As you know, it's a linear function with a negative slope, therefore it'll start from quadrant 2. It'll cross the x-axis at x equals 1 and move towards the quadrant 4. This function will start being positive. It'll cross the x-axis at the root and it'll change to be negative. Therefore, this root, in the first case it is negative 1, and in the second case it is 1. This is called an odd root, where you see the graph crossing the x-axis and changing its sign. The second example we'll look into is the quadratic function, and in this case we'll also extrapolate to say any even degree polynomial. Here we're not going to look for a slope. Here we're going to look for a leading coefficient. So the leading coefficient is the coefficient of the expression with the highest degree. In this case, since it's a quadratic, therefore the highest degree is x squared, and its coefficient is 2, therefore the 2 is the leading coefficient. In this case, negative 2 is the leading coefficient. So if the leading coefficient is positive, in this case y equal 2 into x plus 1 squared, that quadratic function will open up, or will show a concavity upwards, as you see here. And the function will start from quadrant 2 and will finish in quadrant 1. It'll not cross through the x-axis, it'll barely touch the x-axis, it'll touch the x-axis only at x equals negative 1. And here we see that the function starts positive, does not cross the x-axis, and stays positive afterwards. In the second case, where the leading coefficient is negative, as you see here, notice how the function now opens down. The quadratic function opens down. And consequently, we'll see that the function will start negative in the quadrant 3, and then it does not cross the x-axis. It touches the x-axis, and again does not cross the x-axis, and stays negative in quadrant 4. In this case, the root, negative 1 in this case, negative 1 in this case as well, this is called an even root. And as we're drawing, we see those two shapes at that even root, where the function forms a curve that does not cross the x-axis. In the third case, we're looking into an odd degree polynomial. I had to distinguish between a linear and any other odd degree polynomial, because as you'll see from the shape, that the odd degree polynomials that are beyond linear, that are with a degree larger than 1, they will have a curvature change. Whereas in the linear, as we have seen previously, there was no curvature change as the function crosses from negative to positive or from positive to negative in the second example. So going back to the odd degree polynomial, again we'll consider the leading coefficient, the first one being positive, the second one being negative. For a degree 3 polynomial, in this case I'm going to take y equals 2 into x plus 1 cubed. We know that the root is negative 1. We could state that here, root x equals negative 1. Same thing for the other example. But here we notice that the leading coefficient, which is equal to 2, is greater than 0. Odd degree polynomials, they will always start when their leading coefficient is positive from quadrant 3, cross through the x-axis at the root, and go to quadrant 1. So you notice that the graph of the function, it will start negative, cross through the x-axis. It shows a concavity change. That's very important. And then changes sign to be positive. In the second case, where the leading coefficient is negative, in this case a equals negative 2 less than 0, the function has a vertical reflection. So we have a function that is starting in quadrant 2, crossing through the root and reaching to quadrant 4. The graph starts positive, crosses through the x-axis, you will see a concavity change, and then the sign changes to negative. I'm sorry for that mistake. So we see a negative sign. Sign changes from positive to negative. And therefore, the root here, which is negative 1 in this case here and here, that root is an odd root. So for an odd root, we will see a sign change before and after. Even root, we will see no sign change before and after. As for a conclusion, I'm here trying to summarize it and leaving a number line to help us also see how we could represent the sign change or not, the no change in sign on a number line. So for a linear or an odd degree, we see a sign change before and after the root. These are the examples we've seen before, y equals x plus 1 and y equals negative x plus 1. And as you see here, the negative 1 being the root, and here 1 is the root. In the case where y equals x plus 1, the function starts in quadrant 3 and moves to quadrant 1, so it starts negative, then changes to be positive. Here, in the second example, we'll see the opposite with y equals negative x plus 1. The function has been vertically reflected, so the function will start positive in quadrant 2 and cross the x-axis at x equals 1 and move to the quadrant 4 where it becomes negative. The second example here, where the degree is 3, so we're moving into odd degree polynomials. Again, here we have the case where the leading coefficient is positive, leading coefficient is negative, and again you see the sign changes. You could refer back to the drawings and you can explain why there is that sign change. And that is the graph behavior. Notice how with a linear function, the graph behavior behaves like a line. It just crosses through. Whereas with odd degree polynomials, at the root, you notice a change in curvature. That is very important to notice and to draw when you are drawing these functions. So we have a change in curvature before and after the root. As for a quadratic or an even degree polynomial, in this case, we don't have to consider quadratic or even. We can just say even degree polynomials. They will all behave the same. We notice that the sign stays the same before and after. So in a function where y equals negative 2 into x plus 1 squared, the root is x equals negative 1, Since the leading coefficient is negative, a equals -2, the quadratic function opens down, and it starts negative in quadrant 3. It reaches the x-axis at the root and then curves back down to go to quadrant 4 and stays negative. And that would be the number line representing that scenario. So x equals -1 is the root, but the sign before and after is the same. In this case, y equals 2 into x plus 1 squared. The root is still -1. As you can see in that diagram here, we have the function opening up. It starts positive, it reaches the x-axis at the root and then goes back up to stay positive. And this number line here represents that same scenario, where the root is -1, the sign before is positive, after stays the same, positive. As for the graph behavior, for whatever the degree is, 2, 4, 6, etc., this behavior is always true for all even degree polynomials. The function either opens up or opens down. It touches the x-axis, it does not cross.